Hello, Integrated Math 3 and Integrated Math 3 Plus. Welcome to lesson 16-1. We've played with all kinds of functions. We've played with exponential functions and logarithmic functions and rational functions and radical functions and polynomial functions. We've played with a lot of functions. Today, though, starts a new unit. We're going to start exploring a different kind of function, but it's still a function nonetheless. To get this party started, we're going to look at a Ferris wheel. So Tao and Jennifer love to ride Ferris wheels. I like to ride Ferris wheels too, even though I'm afraid of heights, which is a weird thing, but there you go. So their favorite Ferris wheel has 100-foot radius. So from the center, let's see if I can do this right. I can do this. So from the center coming out is 100 feet, which means it's actually 200 feet from bottom to top, isn't it? And it revolves slowly enough that they can just step into a car from the loading platform about 10 feet off the ground, and they sit down as the wheel continues to turn. So the wheel doesn't actually stop. You just get on the loading platform about 10 feet up and hop on, which means actually, if that's 10 feet on the platform, 100-foot radius, my gosh, you're like 210 feet at the top of this thing. That's a big wheel. The location of the car as it travels along its circular path can be modeled by a function where the height of Tao and Jennifer's car is dependent on time. So what we're going to do is we're going to play the animation here to kind of investigate that a little bit. Hang on. Sorry, I got to get my play button back. There it is. So we're going to play this. You're going to want to have question number 1 out on your student activity sheet. On student activity sheet 1, we're on question number 1. So here's the deal. They're going to ride the Ferris wheel. Now the Ferris wheel is moving counterclockwise from our perspective here. So Tao and Jennifer step onto the platform. And at the beginning, before they've even gone anywhere, they just sat down on it. They are 10 feet up, right? Because we said the platform was 10 feet up in the air. So what I'm going to do is I'm going to click this button, and you're going to want to keep track of this on your piece of paper. And we're going to see as time goes on how high up in the air they are. So I'm going to hit this button. So 0 seconds, they're 10 feet up, right? The platform is 10 feet up in the air. So if I hit the button once, then after half a second, they're already up here and they're about 39.3 feet in the air. Again, you're going to want to make a little note of this put a little dot there or something like that at half a second on your student activity sheet on question number 1 on your graph. If I go all the way to 1 second, though, they're halfway up already. So after 1 second, they've done a quarter turn. They're about halfway up height-wise, and they're sitting at about 110 feet because remember, the radius was 10, but the platform's 10 feet off the ground. At 1.5 seconds, they're at about 180.7 feet. After 2 seconds, they're halfway around the wheel. They're all the way up at the top, which puts them at a height of 210 feet. Now, they're going to do 2 complete trips around the wheel, by the way. We're only halfway around the first trip. They're going to do 2. Let's keep going. So if I keep going, then at 2.5 seconds, they're at 180.7 feet. Oh, we're coming back down. After 3 seconds, they're down to 110 feet. After 3.5 seconds, they're down to 39.3 feet. And after 4 seconds, they're back down where they started. And so you can see they went up, they went down. And again, my x-coordinate is time. At this point, we're saying that is time down there. But remember, they're doing a second round. They're going to go around twice. So we're going to hit the button again. 4.5 seconds, they're back to 39.3 feet. You can see where this is going. At 5 seconds, they're back up to 110 feet. At 5.5 seconds, they're back up to 180.7 feet. At 6 seconds, they're sitting all the way up at the top again at 210 feet. 6.5 seconds in, they're at 180.7 feet. And after 7 seconds, they're back down to 110. After 7.5 seconds, they're back down to 39.3. And after 8 seconds, they're all the way back down to the bottom again. You know, can I just say, I know it said that it's going slow enough that they can get on it, but have you watched how fast this thing is turning? I don't think you can jump on that. That feels like it's way too fast. And it feels a little terrifying if it's flinging you around that fast. I'm just saying. I'm just saying. So a few little things here. Let's go back a little ways. Let's look at where was the car before Jennifer and Tao got onto it, right? So we've done, okay, from time 0, but the wheel was turning before they got onto it. So we don't usually do negative time, but the wheel was turning before they got onto it. So half a second before they got onto it, it was at 39.3 feet. 1 full second before they got onto it, it was at 110 feet. 1.5 seconds before they got onto it, it was at 180.7 feet. 2 seconds before they got onto it, it was up the top at 210. 2.5 seconds before they got onto it, it was at 180.7. 3 seconds before they got onto it, it was at 110 feet. 3.5 seconds before they got onto it, it was at 39.3 feet. And of course, 4 seconds before they got onto it, it was sitting down bottom platform at 10 feet. Does this look like any of our function families that we've done before? Like I said, we've done polynomials, we've done rational functions, we've done radical functions, exponential functions, logarithmic functions. We've done square roots and cube roots and so many different things. I mean, I guess it sort of has some of the higher order polynomials had the wibble wobble in the middle, but overall, this really doesn't look like something that we've done before. So let's go to the next level on this then. This Ferris wheel graph, and we're moving down to question 2 and eventually question 3. This Ferris wheel graph represents a whole new class of functions. The graphs of these functions repeat themselves, right? Because you're on the Ferris wheel, you go up and down and up and down and up and down and up and down, and that's what we do. And so that means that when we graph it, we go up and down and up and down. And because that Ferris wheel doesn't stop, people just hop on and hop off, it does it forever. This graph is actually repeating itself, right? It has a cycle that it repeats itself regularly over regular intervals. This helps with question number 2. So a function that does that repeats itself over successive intervals of a fixed length, so a particular length, and it's going to repeat itself again and again and again and again. We call that a periodic function, which, by the way, should help you answer question number 2. So when you have a function that repeats itself over intervals of a fixed length, then we call it a periodic function. So let's answer some questions about this periodic function of Jennifer and Tao's Ferris wheel ride. And you're going to have to flip the paper over to question number 3, and you can sort of see the questions down here. Sorry, it got blocked off a little bit by my writing tools. The deal is, I would like you to just take a few moments to consider your graph and answer these questions. On number 3, part A, how long does it take to complete 1 full cycle, to do 1 full turn of the Ferris wheel? How long does it take? Looking at our lovely graph might be helpful. What are your maximum and minimum values? How high up? How far down? And does the graph exhibit any symmetry? Is there somewhere that I could fold it, that it would like fold onto itself, reflect onto itself, that kind of a thing? So go ahead and hit pause, jot down your thoughts on question number 1, and then hit play when you're ready to continue. So I don't know about you guys, but I noticed it took 4 seconds to complete 1 cycle, right? From the time they got on till the time they went all the way up and all the way back again. It took 4 seconds to complete 1 cycle. My maximums and minimums. Well, maximum, the highest they went was 210 feet. And the lowest the Ferris wheel goes is 10 feet because, again, they get on a platform that's above the ground. Does the graph exhibit any symmetry? Well, if I kept it going forever and ever to the left and forever and ever to the right, it looks like I could fold it down along my y-axis here. That I could just fold it on my y-axis and it would fold right on top of itself. So yeah, it definitely has some symmetry. In this case, it looks like it's symmetrical along the y-axis. Let's consider a slightly different problem. Don't worry, we'll come back to the Ferris wheel. You ever been to Santa Cruz? You ever gone on the pirate ship ride? I remember as a kid once going to Santa Cruz, getting on that pirate ship, and there was no line. So it would end, and the guy's like, do you want to go again? And my friends and I were like, yeah. So we were the only people on the boat, and I think we went on it quite literally 7 times in a row. I think by the end of that day, I kind of was puking my guts out a little bit because we may have done that with several rides, but I do recall distinctly doing it with the pirate ship ride. Ah, good times, good times. So let's look at the pirate ship ride. Question number 4, you have a graph. Don't worry, I'll help you out with this. But you've been on the pirate ship ride. It swings back and forth and back and forth. So we're going to check out how does their height above the ground vary over time as the boat swings. So again, our x-axis, if you're looking at question number 4, is in time, measured in time. And then our y-axis is measured in height. And because this boat is long, to make it easier, we're just going to use the height of the center of the boat. So you see how the mast comes down in the center? We're going to use that height to kind of help us out, make it easier. All right, so first things first, how long does it take to go back and forth? Well, looks like it takes about 4 seconds. 2 to go up, 2 to come back down. So it takes about 4 seconds for it to reach its maximum height. And again, we're using this middle guy here. So at 0 seconds, we're 0 meters above the ground. We're in meters now, not feet. After 1 second, we're 10 feet off the ground. 2 seconds, we're 20 feet off the ground. 3 seconds, we're back down to 10 feet off the ground. And at 4 seconds, we're back on the ground. But of course, it swings out the other way. It does this all again. 10 feet after 5 seconds, 20 feet after 6 seconds, 30 meters, sorry, not feet, back down to 10 meters after 7 seconds, and back down to 0 meters after 8 seconds. All right, so now that you have this table, here's what I'm going to suggest. I've helped you out with the table here because, of course, you couldn't have got that information any other way. So now that I've helped you out with the table, what I would like you to do is on question number 4 of student activity sheet number 1, can you graph this? Can you plot these points? Connect them up and see what happens. So go ahead and hit pause to plot your points and then hit play when you're ready to check your work. All right, let's keep the party going. So did you plot your points? I did. And here they are. Oh, so pretty. Maybe you've done the pirate ship at Great America, the Revolution. That one goes upside down. I don't do that one. I hate losing everything in my pockets to the water down below. So I just stick to the one in Santa Cruz. It doesn't make me go upside down, and it doesn't make everything fall out of my pockets, which is good. It's kind of fun watching the pirate ship one at Great America and watching like rain as things fall down from above into the water below. It's kind of fun to watch. Don't know about riding it, and I'd be upset if I lost my stuff, but it's fun to watch. So here is our lovely graph. Now, of course, we only plotted up through 8 seconds, but clearly we can see a pattern here. So I went ahead and kept my graph going all the way to 12 seconds because we could totally see after 8 seconds, we're like, oh, it's going to do it again and again and again and again, forever and ever. Yay. So the graph describing the height of the center of our pirate ship is also, you can see, a periodic function. And it looks very similar to our Ferris wheel problem. I mean, there's some differences, but golly, it's awful similar. These are what we call sinusoidal waves or sinusoidal curves. They kind of look like sound waves, and there's a reason for it because sound waves are based on sinusoidal curves. Sinusoidal curves are members of our new function family for us called trigonometric functions. These trigonometric functions, just another class of functions that we're adding on to all our stuff. Now, many situations are modeled by trigonometric functions. Lots and lots and lots of them. I mentioned sound waves. That is one of only a few. And of course, you can see your Ferris wheel on your pirate ship definitely have that trig function action going on too. So let's see if we can take this a little further. If this sounds familiar, your trigonometric functions, they should, because you studied trigonometric ratios when you were dealing with right triangles in previous math classes, like in Math 2 and when you took geometry last year. So you remember if you have a right triangle and you're like, oh, here's my right triangle. Ooh, that's a bad color. Maybe I should use a color that we can actually see. Oh, here, let's do this. Let me erase that. That's sad and pathetic. I'm going to fix that. So if I come over here and remember when you had a right triangle, the hypotenuse was always opposite the right triangle. You remember that? Hypotenuse was always the guy opposite the right triangle. And then there was if I was dealing with like angle A, then the opposite leg was over here and the adjacent leg met next to it over here. And yeah, this whole trig thing should sound familiar because you did trig ratios. You remember sine, cosine, and tangent. They're back. Yeah, you remember SOHCAHTOA? Good days, good days. Remember how the sine of angle A is the opposite leg over the hypotenuse? So we called it SO. I'm going to bring my pen back. So we called it SO, right? Sine is opposite of our hypotenuse. And then the cosine of angle A was the adjacent leg over the hypotenuse. So we're like, oh. And then the tangent of angle A was the opposite leg over the adjacent leg. So we were like, TOA. And remember how you use those to help you find stuff on your triangles? It was really cool. And you used a calculator because calculators are good for you, like vegetables. We're going to be taking these little guys, your sine, cosine, and tangent functions, your sinusoidal curves, all that good stuff, and your functions, and we're going to go a little next level with these bad boys. How's that? Yeah. They are super, super useful. They're really useful for prediction purposes just because they repeat themselves, right? You know that if you miss the pretty purple car you want to get on the Ferris wheel, it's cool. You know after 4 seconds, if you wait, it'll come back to you and you can hop on it again. Unless somebody else got on there first, in which case that's just rude. So we're going to investigate some stuff with these periodic functions. Some new topics are going to come into this. The length of the cycle, how tall our waves are and the functions are. And of course, we'll continue discussing about domain and range, and symmetry will come back into this as well. So, erase all that. Get my pencil back. Come back over. So let's come back to our Ferris wheel problem here. If we go over student activity sheet number 2, we're going to mess with the Ferris wheel. Are you ready? We're going to mess with the Ferris wheel. Question number 1. There are a lot of questions to be answered here. So let's start just by talking about this first guy right here. You have 2 graphs sitting there. Don't worry about Ferris wheel graph 2. We'll get there in a minute. Let's deal with Ferris wheel graph 1. First things first, domain and range. Well, these aren't that bad, really. Domain, because we said it's going to keep going up and down and up and down. And before you got there, it was going forever up and down and up and down and up and down. So in this case, then, I'm going to say, and I'm going to write it up here where I've got some space. I'm going to say that my domain, you can say all real numbers, or if you don't want to use words, all real numbers. Remember that there are different ways you could write it. You could say negative infinity to infinity. That was fine. Or if you want to use words, all real numbers, that's cool too. Let's talk about our range for a second here. Now the range is up and down, right? Domain is side to side, range is up and down. I don't go forever up and forever down. You remember you guys told me that we had a minimum at 10 and we had a maximum at 210. That the lowest point I get to on the Ferris wheel is 10 feet up when I'm at the platform. And the highest is when I get to the top of the Ferris wheel and I'm at 210 feet up. So this means that my range is from 10 to 210. And notice I'm using brackets this time because I actually do get to 10 feet and I do get to 210 feet at my lowest and my highest points. But there are some new words there. So if you'll notice underneath Ferris wheel graph 1, like, yeah, we got the domain, all real numbers, it goes forever right, forever left. The range is from 10 to 210. It's as low as we go, as high as we go. But there are some new words here. Period, midline, and amplitude. Shall we discuss those? Yeah, I think we need to discuss those. So let us discuss. Let's talk about the period. Remember how you guys said that there was an interval after which it started repeating itself? So from bottom to top, back down to the bottom, it took me 4 seconds on the Ferris wheel, and then bottom to top to bottom, another 4 seconds, bottom to top to bottom, another 4 seconds. This is a really important characteristic of our sinusoidal graphs. the y values repeat each other, right? After a certain amount of time, the y value starts repeating itself. So the smallest interval on x that we need to complete one cycle of the graph is what we call the period. Well, for this particular problem, I'm going to scroll down just a little bit. There we go. That means for this particular Ferris wheel problem, my period is 4 seconds. It takes 4 seconds from when I get on at the bottom to go all the way up to the top and all the way back to the bottom again. And you can measure it from all kinds of places. You can measure bottoms to bottoms. You can measure tops to tops. You can even pick a point in the middle. Just be careful and make sure if you're picking an upward point, you pick the next upward point. But this is the period of the function. How long does it take for the dumb little thing to start repeating itself? And in this case, that is 4 seconds. So like I said, you can count from bottom to bottom. You can count from spots in the middle. You can count from spots at the top. It doesn't matter. It takes 4 seconds. All right, whichever one of these you pick, it's going to take 4 seconds to do one complete cycle. So the way we write that, you could have written for your period, you could have literally written 4 seconds. That would have been fine. But another way of doing it is saying that, hey, all I have to do is add 4 onto my x and I'm back where I started, so we can actually write the period as f of x equals f of x plus 4. That my function is going to be the same every 4 seconds that I add on to it, every 4 that I add on there, and we call that p for period. So again, you could have said the period is 4 seconds. You would be correct on that. But a more proper way of writing it would be to say that f of x equals f of x plus 4. Because if I add 4 seconds on, I'm right back where I was 4 seconds ago. Got that down with the period? It's a cool trick. So you can actually put your period right there inside of your function. F of x equals f of x plus p, p being your period. It's a more proper way of writing it. Midline. Midline is exactly what it sounds like. And I'm going to pause it for a minute here. Hang on, I hit pause and I missed it. Midline is exactly what it sounds like. It's the line in the middle. It literally is exactly that. So remember how we said the lowest was at 10 and the highest was at 210? Well, where would be the exact middle of that? Well, the exact middle of that is 110. So I would say that my midline is y equals 110. This is easy to see because you're like, okay, what's halfway between 10 and 210? If you're struggling, keep in mind that you're literally finding the average of your maximum and your minimum. So if my maximum is y equals 210 and my minimum is y equals 10, I could just add those together and divide by 2 to find my midline. Please notice for your midline, you must have a y equals on it. It's a line. You just can't tell me, oh, it's 110. That's a point. That's a number. If I'm talking about a midline, I need a y equals on that midline for my sinusoidal. So it's literally the middle line between my minimum and my maximum. So just finding the middle. And again, an easy way to do that is just to add these two together and divide by 2. Yay. One other little thing is that last little thing that you're talking about is amplitude. You've probably heard the word amplitude before. And in fact, you may even have a clue what it means. For our purposes here, a midline helps us find our amplitude. So periodic functions have an amplitude, and that refers to how far above the midline our y value goes. Well, check it out. We already said, so you kind of need to find the midline first. We said our midline was at y equals 110 feet. But we said our maximum was all the way up here at 210. So that means I need to, I can just subtract 210 minus 110 and find that's 100 feet. Another way you can find the amplitude, let's say you didn't have the midline and you're like, I don't know what the midline is, but I need the amplitude. Remember how in order to find the midline, how we added our maximum and minimum and divided by 2? That means in order to find your amplitude, you subtract your maximum and minimum and divide by 2. So if I did 210 minus 10 and then divided by 2, that's going to give me my amplitude. So in the case of this particular problem, looks like my amplitude is about 100 feet. Yay. All right, so now that I've helped you out with question number 1, or with Ferris wheel graph number 1, I'm going to erase all my stuff here. Then I've helped you out with that. Can we go to Ferris wheel number 2? There's a second graph. We're going to pick up the pace on our Ferris wheel, which is a little scary because I kind of felt like that first Ferris wheel was moving a little fast. It was a little scary, but it's cool. Let's talk about the Ferris wheel. Let's say instead of taking 4 seconds to do one full revolution, what if it only takes 2 seconds? Okay, that was terrifying. And again, it was doing it before you got there. Oh my gosh, that thing is moving so fast. I would wet myself on that Ferris wheel. That's moving too fast. Wouldn't it like fling people off? I hope they have you like buckled in really good, because otherwise people are going to go flying off the Ferris wheel. That's bad. So what's changed here? What's changed? What's remained the same? All that kind of stuff. Hang on. All right. You have both of these graphs sitting on your paper. I would like you to go ahead and finish off question number 1 and answer all that information for Ferris wheel graph 2. Your domain, your range, your period, your midline, your amplitude. Answer them all. Go ahead and hit play to work that out on your paper, to make notes on that, and then hit pause to put that on your paper, and then hit play when you're ready to check your work. Now, I hope you noticed almost everything was the same, but not quite. My domain was the same. My domain, it goes forever to the right, forever to the left. We just didn't do that, but we could have gone forever right, forever left. So my domain would be all real numbers. Up and range is up and down. Well, it's still lowest it's going is 10 feet, and the highest it's going is 210. So my range is still all real numbers from all real numbers from 10 to 210. But what changed? Your period did. Yeah, the original had a period of 4 seconds, but this new guy has a period of 2 seconds. However, notice because your amplitude and your midline depended on your maximum and minimum, those didn't change either, since our maximum and minimum didn't change. So my midline is still 110, y equals 110, pardon me, and my amplitude is still 100. So the period is what changed this time. That was what was different. Everything else pretty much stayed the same. Yeah. Now, of course, let me go into this a little more. This whole Ferris wheel deal, we've called it a sinusoidal function, a sinusoidal curve or wave, trigonometric function. This particular example is what we could also be called a circular function, because it's literally a periodic function that we create by wrapping around a circle, which we did. We had a big circle that we were wrapping around. So the domain of these functions can be measured in is the measure of the angles of rotation, right? You know that all the way around a circle is 360 degrees. You've done that before. That's not a surprise to you. But as we go into our study of trig functions, we're going to start playing with the height of our Ferris wheel as a function of our angle of rotation. As I said, one full rotation is 360 degrees. Half a rotation would be 180 degrees. You know how this goes. But this means you could actually do more than 360 degrees, right? Because you could rotate around and around and around and around. And of course, if you went backwards, you could have negative angles of rotation. So let's play with this just a little bit. So let's talk. What is an angle of rotation? An angle of rotation can be described by any positive or negative value. It can include fractions and decimals. It can do all that stuff. When we measure an angle of rotation on a coordinate grid, I'm going to scoot this down a bit, the angle is in standard position when its vertex is at the origin and the terminal side of the angle rotates counterclockwise from the x-axis. So the x-axis is always one side of my angle, and then that other side of my angle rotates counterclockwise, just like our Ferris wheel did, around the origin. I mean, you're used to being told that an angle is two rays with a common endpoint. You've used protractors to measure them, all that good stuff. Angles that measure, and usually when you used a protractor, you did angles that were less than 180 degrees. But of course, we're saying we can go all the way around to 360 and beyond at this point. So let's play with that just a little bit. So this x-axis is what we would call the initial side. And then as we rotate counterclockwise, we call this other guy the terminal side. So here we have a 60-degree angle. We start on the positive side of the horizontal axis. So we start on the right of our x-axis, and that's my initial side. And then I rotate up 60 degrees counterclockwise. So if I had a protractor, I would measure that out and be like 60 degrees. There's my terminal side. And it marks the terminal side of the angle. We call that angle in standard position because the initial side is the positive x-axis and the vertex is on the origin. So this is an angle of rotation. Now, of course, we can take this further. I don't have to just do 60 degrees. I can go further. I can go all the way around. Oh, look at that. Here's a 310 degree angle of rotation. Started here, went past 60. You can see straight up, that would be 90 degrees, right? Here, from here to here, be 90 degrees. If I kept rotating all the way to here, if I had a straight line, that would, of course, give me 180 degrees. But we took it further. You can add on another 90 degrees. So 180 plus 90 gives you 270 degrees. But we went 40 degrees past that. And we got all the way over here to 310 degrees. So yeah, you can rotate pretty much any number you like. So this is a 310 degree angle. But I want to point something interesting out to you, which is going to help you with question number 2. Are you ready? And eventually question 3. Instead of going clockwise, I could go counterclockwise. And when I do that, then I have to, if I go clockwise, we're used to going counterclockwise, right? We're used to going this way. But if I go clockwise, it's the wrong way, so to speak. So that means my angle of rotation becomes negative. So this means my angle just became negative 50 degrees. So if you rotate an object in the negative angle measure, you've rotated it. So if you see a negative angle measure on your angle of rotation, you just went clockwise instead of counterclockwise. But here's what's interesting is take a look. This is going to help you out with question number 2. Take a look at this. So here's my negative 50 degree angle of rotation, but I'm going to bring back my positive 310 degree angle of rotation. Guys, I ended up in the same spot, the exact same spot. One full rotation is, of course, 360 degrees, right? If I added 360 onto that negative 50 degrees, if I added on 360, it would give me 310. So the terminal side of my negative 50 degree angle is in the exact same spot as the terminal side of my 310 degree angle. Angles that do that have the same terminal side, are said to be coterminal. Yeah, I think I just helped you out with question number 2. Part A, where it says list 3 angles that are coterminal with negative 50 degrees. I think I just gave you one by pointing out you could add 360. But remember, we can rotate as many times as we like. I could add 360 as many times as I want to. So here's what I would like you to do. Question number 2 says to list 3 angles that are coterminal with negative 50 degrees. I've given you one. Go ahead and hit pause to give me 2 more, and then hit play when you're ready to check your work. All right, are you ready to check? You ready to see how you did? You ready? Are you ready? Are you ready? I bet you're ready. Come on, come on, come on. I got more than 310. So we had negative 50 degrees. I added on 360, and that gave me 310 degrees. Yay! But I said you could add on 360 as many times as you want. I could go around again. So add 360 to 310, which gives me 670 degrees. I could do it again, add another 360 degrees, and that means I get 310 plus 2 times 360 degrees gives me 720 degrees. Yay! 1030 degrees. So basically, this helps me answer questions. So hopefully you got something similar to this on part A. Part B is asking you to write an algebraic expression that would give you all of them. Well, fine. I could just say 310 degrees plus n times 360, right? 1 times 360, 2 times 360, 3 times 360, 4 times 360. I could add 360 as many times as I like. And this is kind of a shortcut way there on part B to help you write that. All right. I think you have the idea. So here's what I want you to do. I want you to go over to question number 3 on your student activity sheet. And I would like you to work these out. You may want to use a protractor to help you out. You don't have to if you want to eyeball it. I'm not going to be checking and measuring this mess. But go ahead and start by sketching the angle in standard position. And then give me one more angle that is coterminal with the given angle. As we pointed out, there's more than one right answer here, but just give me one, okay? Go ahead and hit pause to work out question number 3, and then hit play when you're ready to check your work. So I don't know about you guys, but I mean, I kind of use the 90s, right? This is 0, 90, 180, 270, back to 360. Kind of help me get an idea of where to graph these things, right? And I kind of cheated. I'm not going to lie here. I use this over here. So here we go. I always have the x-axis as one side of my angle, and 110 degrees is about here. I realized I could subtract 360 from that, and I could get an angle of negative 250 degrees. Or you could have added 360 to this guy and you could have given me 470. That would have worked too. If I come over here to B, I notice 330. Well, that's 90, 180, 270, but not quite to 360. So it was out here. So remember, one side is the x-axis and the other side's out here. I realized very quickly it's coterminal with negative 30 degrees because if I subtracted 360, or if you added 360, you could have told me it was coterminal. Oh, if I add 360, it's coterminal with 690 degrees. That also would have been okay and would have worked just fine. Too far, too far. There we go. My pen's a little sensitive. Over here, I have negative 120 degrees. So fine, this would be negative 90, but not quite to negative 180. So it would have been out here somewhere. If I add 360 to that, I get 240 degrees. I'm going the other way. This lovely guy over here, 225 degrees. So I was like, all right, that's 90, that's 180, not quite to 270. So here's my 225 degrees. It is coterminal with a negative 135, or if you'd added 360, which you could have done, if you'd added 360, that would have given you a positive, oh gosh, I have to think, 585 degrees. I think I added that right. Yay. I hope I did. All right, guys, I think you got the idea with this coterminal stuff. So we have just a little bit further we're going to go. Okay, maybe a lot further, but a little bit further. Come on, you got this. We're going over to question number 4. So now that you understand a little bit about these angles of rotation, here's what I'm going to do because it's a Ferris wheel, I'm swinging it up. But remember how we were looking at the height at any point in time on the Ferris wheel? When I draw in that height, I end up making a right triangle. Isn't that pretty? Isn't that beautiful? So I made a lovely right triangle. So instead of thinking this is a real Ferris wheel, what we're going to do is we're going to kind of shift it so that the center is on the origin, and we're going to assume that our radius is 1. It just makes things so much easier to deal with. When we do this, we call it the unit circle because our radius is 1. So we're just simplifying it by saying, fine, instead of the whole big old 100-foot Ferris wheel, 10 feet off the ground, no. We're just going to put our center on the origin, and we're going to say that it has a radius of 1, just to make things a lot easier for us. So this is called a unit circle because it has a radius of 1 unit. Now, this particular picture that we have here that you also have on question number 4 shows a 60-degree angle in standard position. So we've started here, we've worked our way up, boom, 60 degrees, there it is, and then we drop down for the height right here. This point P is on the terminal side of our 60-degree angle, and it's also on the unit circle. So here's what I'd like you to do. I want you using some of your geometry skills from last year, I'd like you to find point P on the, I'd like you to find your height at point P. Yeah, that's what I want. I want the height at point P. If you need a hint, I'm going to give you a hint. If you're like, oh my gosh, if you need a hint, I've got a hint for you. Do you remember special right triangles last year? Do you remember them? Do you remember 45, 45, 90 triangles, 30, 60, 90 triangles? Do you remember these guys? I do. Go ahead and hit pause. See if you can find the height on your lovely triangle, and then hit play when you're ready to check your work. You think you're ready for this? Y'all ready for this? Da, 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 da. Going to the next page. Ooh. All right. So this was totally, since I had 60 degrees here, so it's definitely a 30, 60, 90 triangle. I'm going to grab my pen here. I'm trying to find this guy over here. I know what this is. We know that that's equal to 1, right? Because we said it was a unit circle. And so the radius is going to be 1. So I'm like, well, that's 1. So I was like, okay, well, 2x equals 1. So that means that x must be a half, because 1 divided by 2 is a half. I used a decimal to make it easier so I could grab my calculator. Well, now I know what x is. I can find this height over here, right? We said that x was a half. So fine, 1/2 or 0.5 times the square root of 3. So if my height is x root 3, we just said that x was a half. So I'm going to pop that there and grab a calculator. Do the square root of 3, times it by a half, and I get 0.866. Now that you know what the height is, find the coordinates of the point. Find the x coordinate, find the y coordinate. Use this to help you out. Hit pause, find it, and then hit play when you're ready to check your work. Well, I don't know about you, but I noticed that my x coordinate was x, and we already said what x was. We said that x was 0.5, right? Yeah, we did. So fine. That means my x coordinate is 0.5. I'm going to clean this off. It's making a mess. My x coordinate is 0.5, and my y coordinate is what we found earlier, the height, which was 0.866. Because those are the values that fit with our 30, 60, 90 triangle. Now, using this same idea, you're going to probably want to redraw this a little bit down on question number 5. But go down to question number 5. Do all of this again, only let's say that point P, instead of being a 60-degree angle, let's say that point P rotates down a bit to give us a 30-degree angle. Go ahead and hit pause to work that out on question number 5, and then hit play when you're ready to check your work. I'm ready. Are you ready? I'm ready. So that shifted my triangle a little bit, and they didn't draw. I'm going to draw the triangle because I think that'll help you a little bit. So I'm going to redraw my triangle because I've changed it, right? So now this is 30 degrees and that's the 60 degrees. But that means that this is 2x, which we already know, by the way. We already know that x equals 0.5. No, it doesn't. Sure it does. So that's 2x, and that's x, and that is x root 3. So look at what happened here. It looks like when I went to 30 degrees instead of 60 degrees, it looks like my x and y switched, which they did. My x and y coordinates swapped because I flipped around my triangle. So now my coordinates of P, if I'm dealing with a 30-degree angle, are 0.5, because we already know that x is 0.5, right? Because we know that, oh, golly, bring my pen back. We did that earlier. That we already knew that since 2x had to equal 1, that x was going to be 0.5. So that means if I plug it in here and plug it in here, that'll give me my x coordinate and my y coordinate. So they did swap from last time. Ooh, yay. Just a little bit more. We're almost there. Are you sick of this lesson yet? Shh, don't worry. We're just about there. Miss Scott's going a little loopy too. It's fine. It's fine. We're going over to question number 7. Don't worry about 6. You'll get to do it in your homework. So as long as the terminal side of the angle, in this case, our radius, makes an acute angle with the x-axis, we can totally use our right triangle ratios to find the point on the circle, right? Our 30, 60, 90, or 45, 45, 90s. Let's come back, though, to our Ferris wheel situation, though, because remember how we could get bigger than that? What if I have a 135-degree angle, right? I've gone further on my Ferris wheel. I'm over here at 135 degrees. This changes things a little bit. Now I'm going to help you out with some of this. The right triangle is the reference triangle that we're going to use to help us find our stuff. Now, we already know the hypotenuse is 1. We know this. That's not a surprise. But check it out. If a straight line is 180 degrees, 180 minus 135 gives me 45 degrees over here. So the referencing I'm going to use is actually a 45, 45, 90 triangle. Now there's another trick though that happens because look where we ended up. When we were in the first quadrant, x is positive, y is positive, yay! But now I'm in the second quadrant, which means that my x coordinate is going to be negative, but since I'm going up, my y coordinate is going to be positive. So because I'm going left, my x coordinate is negative, but I'm still going up, so my y coordinate is positive. Here's what I would like you to do. I would like you to start by finding the lengths of the legs of this. Use the 45, 45, 90 triangle trick. It was on an earlier page. If you got to rewind a little bit to go back and find it, that's cool. But I want you to find the lengths of the legs of this reference triangle. And then I want you to tell me how you can use those lengths to find the coordinates of P, in its current location. So go ahead and hit pause to do question number 7, and then hit play when you're ready to check your work. So I definitely used the right triangle trick. I'm not gonna lie, it made things easier. So I did that. So 45, 45, 90 triangle. Well, okay. So 45, 45, 90, this was our trick from earlier, right? Our special right triangle. Well, I know the hypotenuse is x root 2, but I also know the hypotenuse is 1. So if x equals the square root of 2, x times the square root of 2 equals 1, if I divide 1 by the square root of 2, I get, on my calculator, 0.700, I can do this, 0.707. And that gives me both of my legs, actually, because on a 45, 45, 90 triangle, it's isosceles, and both legs are going to be the same, and they're both going to be x, which is 0.707. The only thing I want you to watch out for is, of course, we were just saying that the x-coordinate is negative, that the x-coordinate is negative, and the y-coordinate is positive. So please watch out for your negatives and positives. It'll make things easier for you. All right, guys, as always, I hope you found this helpful and I hope you found this useful. You got questions or concerns, please email me or check me out during office hours. I'll help you out. Have a nice day. Bye.